construct power series, what we're going to do is we're going to take successive derivatives of f and then evaluate those derivatives at the center, in this case x equals 0, and divide that by n factorial, and that will give us our an term or our coefficient of our polynomial expansion. So that's what I'm going to do first here for f of x equals sine x. So I'm going to take derivatives of that. So the original function is sine x. The first derivative will be cosine of x. The derivative of that will be negative sine x. And the nice thing about this function is that it's just going to flip back and forth between sine and cosine and not get really complicated looking. So this is kind of a nice one to start with. So we take the derivative of sine is going to be negative cosine x. The derivative of cosine is going to be negative of the derivative of cosine is going to give you negative sine, which is just positive sine. Derivative of sine is cosine x. The derivative of cosine x is negative sine x. And we end up with negative cosine x as the last derivative in our table. So then we evaluate the derivative at x equals 0. So working out that sine of 0 is 0, cosine of 0 is 1, and then we're going to divide that by 1 factorial. That's just 1. Negative of sine of 0 is 0. Negative cosine of 0 is negative 1. So we get negative 1 over 3 factorial because n is equal to 3. Sine of 0 is 0. Cosine of 0 is 1. And then we're going to divide by 5 factorial to get that coefficient. Sine of 0 is 0. And then cosine of 0 is 1. So negative cosine is negative 1 over n is 7. So 7 factorial. So those represent my coefficients. And what I'm going to do is then I'm going to build my polynomial power series. So that power series for any n value approximates the sine x function. And if I take a limit, the limit as n approaches infinity of p n of x, we're going to say that it's going to equal our sine x function. Okay, so that will then, if we took a limit of infinite terms, that will be equivalent to sine x. Okay, but right now we're just going to use a finite number of terms, and we're going to build our p of x function. We'll just generalize it first as p of n. So n number of terms, it's going to be 0, so we'll leave that out, become 1. For n equals 1, the coefficient's 1, so it's going to be 1 over 1 factorial x to the power 1. And then the next term is going to be minus 1 over 3 factorial x to the power of 3. Then it's going to be plus 1 over 5 factorial x to the power of 5 minus 1 over 7 factorial x to the power of 7 dot like that. And it'll go forever. And our P7 then, if I just clean that up, is going to be x. That'll just be x minus x cubed over 3 factorial plus x5, the power part, over 5 factorial minus x7 over 7 factorial. Okay, so that is our series. If we want to just cut it off there, we'll call that P7. So I differentiated, found successive derivatives. I evaluated those derivatives at the center and then divide by n factorial to generate our coefficients. And we can see that the coefficients look like there is some distinct pattern there. And if we want to generalize for that, we can work out a general formula for AN. We'll do that at another point, but for now that we're going to stop here. Now, what have I done? What I've done is I've generated these polynomial series that mimic sine x. So in purple is the sine x. In green is the first two terms, or n equals 3, that follows that sine x function centered at 0. It's pretty close at 0, but it diverges when we get away from, as we move out. So if I use more terms, so if I use the power 5 term, which is in orange, you can see that power 5 terms follows even better and for a larger radius as well. And if I move on to the 7th term, okay, so I have the degree 7 term in blue, you can see that the degree 7 term is really close compared to the degree 5 term. It's even better than the degree 5 term. And as we add more terms, it'll follow that purple sine graph better and better and better. So you can see that even the first 4 terms, it's really indecipherable. It's hard to distinguish sine x from the polynomial near 0. So then we're going to take that series and the first 2 terms of that series, and we're going to estimate sine 0.5. Okay, so we're going to take the first 2 terms. That is going to be just the x minus x cubed over 3. Okay, and that's going to be we'll call that P3 since it's got n equals 3. And that function is going to be x minus x cubed over 3 factorial. And we're going to work out an estimation for sine of 0.5 by using that formula. So we're going to put that in 0.5 minus 0.5 cubed over 3 factorial. And when we do that, we'll do the calculations for that. Okay, when we type that into our calculator, we get 0.47916, and just repeating after that. So that's what it looks like. Now what we're saying is that value that we've calculated is pretty close to sine of 0.5. So the actual value, sine of 0.5, okay, it's equal to 0.47945. It goes forever, and it is accurate all the way to the 3rd decimal point. Okay, the 3rd decimal point is just as accurate as the actual value versus the polynomial series. And here we've only used 2 terms of this series, and we can get an approximation that is very close.